All right, Gen Chem team, today in this lecture we are now getting into electrochemistry, or redox chemistry. So when we look at this idea of redox, there's two I guess portions you could imagine to the expression. One is the first bit, the red, I guess you could say, and then there's the ox. The RED portion of that term is talking about reduction, and the ox part is talking about oxidation. So that's kind of the slang, right? We're talking about redox chemistry, we're talking about reduction and oxidation. So let's first look at reduction. Reduction basically involves a gain of electrons. And just to show you my sort of shorthand there, we're going to be getting into a lot of electron transfer, electrons moving from one thing to another, i.e. electrochemistry. Going to be writing electrons a lot. So we see this E-1 to symbolize that idea of the electron. And so that's our idea of a reduction, is basically a gain of electrons. So for example, if we had chlorine going to chloride, notice that there's going to be a gain of electrons that's occurring here in terms of our chlorine both chlorines are neutral, while over here both chlorines have one more electron. And we get that from that notion of, the charge, chlorine -1. So both of those chlorines are gaining an electron, and so if we were really to balance out the process, we would have our two electrons as also a starting material, So the two electrons are being given, one to each chlorine, and then each chlorine becomes negative, and as a result, we have now, for each chlorine, one extra electron. Oxidation is the opposite process as far as, instead of, gaining of electrons, we're now talking about a loss of electrons. So, and there's our complementary chemistry that we're going to start to see in this area of electrochemistry. So an example of this could be looking at magnesium. Here we have magnesium going to magnesium plus 2. So just like we had the chlorine going to something negative, as far as a charge is concerned, we have now something similar going to a charge, but notice that the charge is opposite in sign, positive as opposed to negative. And so this would be looking at a loss of electrons. The magnesium on the starting material side is neutral. But here, the magnesium has basically lost 2 electrons. Again, looking at the charge of the magnesium being that +2 state. So it must have lost 2 electrons now to become +2. So if it's losing electrons, that means that those would be then on the actual product side. That those electrons came off of the magnesium, thus producing magnesium +2, as well as then those 2 actual electrons. So that's the introduction of redox chemistry, is this idea of reduction, gain of electrons, oxidation, loss of electrons. And a common mnemonic that I remember all the way technically from high school from my fantastic chemistry teacher, Mr. Daskovich. He definitely pushed me in this direction. Oxidation involves loss, and reduction involves gain. And so it's kind of a mnemonic to help with that process, where we have OIL or IG or oil rig. And in both of these cases, as far as loss and gain, we are talking about electrons. Now that we have a basic understanding of reduction and oxidation, as far as reduction gaining electrons, right? Oxidation losing electrons, we have to now have an appreciation of assigning what's known as oxidation numbers. And so each element whether that element is monoatomic or molecular, basically has an oxidation number. So what are these good for? Basically, these help us to understand the oxidation state of an element, and if basically the element is gaining or losing electrons in a reaction. And that would mean we'd have a change in oxidation state. So basically, the oxidation number is really important because it helps us to understand this idea of gaining or losing of electrons And this is how we can then determine a change in oxidation state in a given particular reaction. So, couple rules I guess we have to kind of walk through. First, elements in their natural uncharged state have an oxidation number of 0. So if we look like at iron solid, for instance, right, it would have an oxidation number of 0, and I can put these oxidation numbers down here in red. Or if maybe we had sodium. Or we could have bromine, or I'm sorry, let's do chlorine. And there's some weird ones out there, right? Like sulfur. Sulfur exists as S8. But these are just all these, elemental states of these sulfur here, kind of the weird one, right? Because it exists as an octamer, or S8. And it also has, again, that 0 oxidation number. So that's the first rule. Monoatomic elements that are charged have the same oxidation number as the actual charge. So if we were looking at like our example above, we had chloride -1. So its oxidation number would be -1. Or if we had sodium +1, now we have that +1 oxidation number, right? And so we can do that with a bunch of these. Oxide -2. Charge has a -2 oxidation number. So monatomic elements, right, that are charged, well, guess what? That is the oxidation number. So we've really been talking about oxidation numbers for a while in the sense of that charge idea. So now we're getting into molecules. We're talking about, elements as they exist in nature with rule 1, monoatomic elements still with rule 2, but with charge. And now we're getting into molecules. It's basically an electronegativity game at this point. So you could say that within this, we could say, part A, the most electropositive maybe we like electronegativity better, the least electronegative. Right. Basically gets a positive oxidation number. That we would predict from charge and the periodic table. So if we think about the most electropositive elements, right, we're really talking about this notion of, group, 1A, as far as, going down the list of hydrogen, lithium, sodium, potassium, etc. We would predict all of these to have basically a periodic charge equal to +1. And so that means that also is then its oxidation number. These are elements that we always find at the beginning of the periodic table, but also at the beginning of a molecule. So we see that a lot in terms of these always having a +1 oxidation number. If we go to group 2A, and so here coming down from beryllium to magnesium to calcium, here the periodic charge would be equal to +2. So that means that the oxidation number for these elements in this row, in this family, is also then +2. And then a third one that we could look to would be group 3A. So here we're jumping across the pond really to kind of the metalloids area with this notion that, boron, aluminum, indium, I should say gallium before indium, gallium, indium, etc. And here we'd kind of look at the periodic charge to be equal to +3. I know that's finicky with the metalloids because obviously they make covalent bonds. But as far as our oxidation number, that still holds pretty true, that we have a +3 for those. So these, or what I would say are go-to elements they always have the same positive oxidation number. So there are these families that we have. And so that splits it up. So in molecules, we have that aspect, right? We have, the first part of a molecule is that most electropositive element. The second part of like the simple, binary molecule would be now the most electronegative. Or least electropositive element. And that element gets the negative oxidation number as predicted by the periodic, charge trend. So if we look at, the most electronegative element, would be fluorine. And fluorine, always has a -1 oxidation number. You could say that the next most electronegative would actually be then oxygen. And where we find it on the periodic table, you would say it's going to have a -2 oxidation number. For, fluorine, this is always, it's always the most electronegative. And then for our oxygen, it's the same unless it's unless paired with fluorine. So if you had OF, for instance, well, fluorine's the most electronegative. So you're going by that idea of electronegativity. So as far as that trend goes, for, our periodic table, that trend is, up and to the right. But we can be a little bit more specific here with, fluorine, oxygen are really on that most electronegative side of things. And then we get to chlorine, nitrogen, bromine, iodine, sulfur, carbon, and then phosphorus. So that's just a little bit more specific with that trend. So that means that we really have two parts, for this idea of simple binary molecules. We're going to have, the more electropositive and that's going to be paired with the more electronegative. And so that's just our simple like binary type molecule. So the oxidation number would be positive for our most electropositive, while our oxidation number is going to be negative for the more electronegative species. Part C, the sum of the formal charge, of the oxidation numbers must equal the charge on the molecule. And that's, same goes with an element, which we talked about already above. So if we look at, let's say, some examples of these simple binary compounds. Such as potassium chloride. If we look at potassium chloride, we have that kind of a beginning part to this, right? That here is our first element. This element is the most electropositive. We have our other second element, and now this is the most electronegative. The charge that we would predict from the periodic table would be +1 for our potassium, while the charge that we would predict from the periodic table for the chloride would be -1. So those are our, periodic charge that we would get by just looking at the element on the periodic table and seeing what it would want to become, really to get to that noble gas electronic configuration. So our oxidation numbers are going to equal that. We're going to have +1 for the potassium, we're going to have -1 for the chlorine, and the sum of those oxidation numbers is equal to 0, which is also, the charge on the molecule. The molecule potassium chloride does not have a charge, and so those oxidation numbers should cancel out so that we have a 0, and they do. Let's look at another example. Let's look at magnesium nitride, or MgN2. So here we can do, the same thing as far as that organization goes of first element and second element. So here is our first. Here's our second with the nitrogen. So this is our most electronegative. And we would predict it would have a -3 charge from the periodic table. And then our magnesium is the most electropositive. And so it would have a predicted charge of +2 from where we see it on the periodic table. And so the oxidation numbers here would then be equal to +2 for the magnesium and -3 for the nitrogen. Notice that there are 3 of those magnesiums, so that's why we multiply by 3 here, to really just represent why we actually have that stoichiometry of 3 to 2, is now we have the sum of all the magnesium oxidation numbers, and if we do the same thing for the nitrogen, there are 2 of them there, and we get a -6. So there's our sum of all the nitrogen oxidation numbers. And if we still again look at that, right, our sum of the oxidation numbers is still equal to 0. So again, that charge still balancing out. So those are some simple binary molecules as far as looking at oxidation numbers. So now in more complex molecules, or ones that contain transition metals. Remember, transition metals can have more than one type of charge. Right, iron could be +2 or +3. Copper could be +1 or +2. So in more complex molecules, the method should be, starting with step 1, assign oxidation number for your go to positive element or electropositive or most electropositive element. And then the second step would be to assign now the oxidation number for our go to negative element or the most electronegative. And if we think about just our kind of molecular structure, right, the positive is always first element in the molecule for that most electropositive, and for most electronegative, that's going to be usually our last, really, element in the molecule. There are some exceptions, but for the most part, that's how we see it. Now, with what is left over, we want to assign the oxidation number for the element that is a transition metal. Or an element that can expand its octet. Remember that before an element in the principal quantum level greater than or equal to 3. So save those for last. So assign the oxidation for those elements last, and their oxidation number will balance out the sum of the oxidation numbers and the charge on the molecule. So those are the three different sets of rules that we kind of want to go through. So as some examples, we could start off with maybe phosphoric acid. So what I see is, step 1, where I would have a +1 charge, right? That would be my go-to electropositive, right? Hydrogen's in group 1. It's always going to have a +1 charge to it. If I look at oxygen, it's always going to have a -2. It would be our go-to electronegative. And so if we look at then the oxidation numbers, we would have +1 for our hydrogen, and we would have a -2 for our oxygen, right? This would be times 3 because of our number of hydrogens, so we end up with a total of a +3 sum of oxidation numbers for the hydrogen. If we do the same thing, we would multiply our oxygens by 4 to get its total sum of its oxidation numbers, which would be a -8. And then we're saving the phosphorus to balance out our charge. And so if we look at the balancing out of the charge, we have a total of -8 on our oxygen side. We have a total of +3 on our hydrogen side. And so that means the oxidation number for the phosphorus is +5. So just with some of that kind of language there I'm using, if I have parentheses, that's the element oxidation number. If I have the brackets, that would be the sum of the elements and all of those oxidation numbers. So you see some things in parentheses, that's the individual element oxidation number, and then you see brackets, which is then the sum of those. So for our hydrogen, would have an oxidation number equal to +1. For our phosphorus, its oxidation number would be equal to +5. And then for our oxygen, its oxidation number is equal to -2. So those are the steps. Step 1, go to electropositive. Step 2, go to electronegative. And then step 3, what's left over? And we use that to balance out the actual charge on the molecule. Let's do a couple more examples. So let's look at dichromate, or Cr2O7 -2. So here we have a molecule that actually has a charge. Notice that above we were balancing out the charge to be equal to 0 because the molecule phosphoric acid had no charge, but here we actually have a -2. So there's no electropositive element as far as a go-to electropositive. So we would start with our oxygen with that -2 charge, right? It's the most electronegative, right? And it's definitely one of our go-to elements for that notion. If we look at the chromium, well, this is really transition metal. So we want to use that to balance charge at the end of the day. So if we look at the oxygen first with our oxidation numbers, right, we have our -2 for the oxygen, actually 7 of them, 7 oxygens, and so that would give us a total of -14 for our oxygen sum of oxidation numbers. And so that means that for the chromium side of things, right, in that nature of balancing out the charge, that means that we would have to have a total of +12 in order for that. Remember, our charge here is equal to -2. So we have a total of -14 from the oxidation numbers of oxygen. So that means we must have a total of +12. And then in going back to the oxidation number individual, right, we would have to divide by 2 since there are 2 chromiums there. So each one would have an oxidation number of +6. So our oxygen its oxidation number is equal to -2, and we see that quite a bit since oxygens are very electronegative. Chromium, its oxidation number in this case is equal to +6 as a result. So still, a simple molecule, binary, 2 elements, but one of those elements is a transition metal, so that's why we still want to wait till the end as far as assigning its oxidation number. And then this is also a molecule that actually has charge, so we want to make sure that we show that charge on the molecule by the subsequent difference in the oxidation numbers. Let's do one more example of this. So here we have potassium permanganate, get no charge on the molecule here. So we have our most electropositive potassium is going to be that +1. That's one of those go-to group 1A elements. We have our oxygen as well. We see, again, like I said, we see that a lot for our go-to most electronegative. And then we're going to use the manganese to balance. Right? Again, it's a transition metal as well. So, again, there's steps 1, 2, and 3. So, as far as our oxidation numbers are concerned, our potassium is going to have a +1. There's only one of them there. Our oxygen is going to have a -2 individually. There's 4 of them, so we're multiplying by 4 to give a total of -8 for its sum of oxidation numbers. And then we have the manganese, which is trying to balance out now the rest of the process. So we have a total of +1 from the potassium. We have a total of -8 from the oxygen. So that means our manganese must be +7. And so it's this sum here which balances out to be 0, again, since molecule is neutral. So if there's charge, it would have to equal the charge. If there's no charge, then it has to be equal to 0, like we see in this particular case. Again, 1, 2, 3, electropositive, then electronegative, and then the middle element, or the transition metal element, or element that has the ability to expand their octet. We then have that as the last step to balancing out the oxidation numbers. There are some interesting ones out there. I guess we'll do just one more as far as that is concerned. So sodium hypochlorite, this is just a one that doesn't fall into all the boxes that I've drawn so far in this lecture. It kind of is written just a little bit differently than what we see in a lot of other molecules. But we can still follow the rule sets, and we should still be good. Right? We still have our go-to electropositive element with the sodium, and it having that +1 charge as far as its prediction on the periodic table. And then we'd have to pick, oxygen versus chlorine. But oxygen is the go-to here. It's the most electronegative. So it would have a -2. The chlorine here is the balance. And notice that this is also, following our rule number 3. This is an element that's in the n is greater than or equal to third periodic row. So this is an element that can expand its octet. So that's why we leave it as the third step. So our sodium here has a +1 oxidation number. Our oxygen has a -2 oxidation number. And then our chlorine, which we don't think of as being positive, actually has a +1 oxidation number, again, to balance out the charge. So that balances out that charge since the molecule is neutral. So that's our assignment of oxidation numbers. Oxidation number assignment is crucial in going forward into the next lecture, which is balancing redox reactions. Balancing redox reactions is extremely tough. I'm not going to sugarcoat it. It's not simply balancing out elements. That would be easier, much easier. Not only are we balancing out elements, we're also balancing out charge and electrons. And so from that angle, these balancing of redox processes can get tricky. We also have different mediums and different rules of balancing depending on if we're in acidic medium or basic medium. So a complex lecture topic coming up, but we had to have this skill set here, assigning oxidation numbers. That is crucial to the first step of balancing redox reactions. So practice up here, and then we can apply it to balancing redox reactions next.